what they actually are, there is a place in the universe where the laws of physics stop making sense, where time slows to a crawl, light can't escape, and matter gets stretched like taffy until it disappears entirely. We call them black holes. But almost everything you think you know about them is either oversimplified or just plain wrong. Today, we're going to fix that. By the end of this video, you'll actually understand what a black hole is. Not the movie version, the real one. And the real version is somehow even stranger. Let's start with the name, because it's a little misleading. A black hole isn't a hole. It's not a tunnel, a portal, or an empty void cut into space. It's the exact opposite. It's matter packed so densely that gravity wins completely. Here's how one forms. Massive stars, ones many times bigger than our sun, spend their lives in a constant tug-of-war. Nuclear fusion in the core pushes outward, while gravity pulls inward. As long as fusion keeps burning fuel, the star stays balanced. But eventually, the fuel runs out. And when it does, gravity wins instantly. The core collapses in on itself in a fraction of a second, so violently that the outer layers of the star are blasted away in a supernova, one of the brightest explosions in the universe. What's left behind, if the core was massive enough, isn't a planet, a star, or even a normal object. It's a point of matter crushed down so small and so dense that it warps the fabric of space and time around it. That's a black hole. So if a black hole isn't a hole, what's the black part? That's the event horizon. And this is the single most important concept to understand. The event horizon is a boundary in space, not a physical surface. It's the point of no return. Cross it, and no amount of speed, thrust, or energy can ever get you back out. Not because of some force field, but because the space itself is falling inward faster than light can travel outward. Think about that for a second. Light is the fastest thing in the universe. Nothing outraces it. But inside the event horizon, space itself is moving inward so fast that even light, moving at full speed in the outward direction, still loses. It's like trying to swim upstream against a current that's faster than you can ever swim. That's why black holes look black. It's not that they're absorbing light like a sponge. Light literally cannot escape once it crosses that line. Anything inside is, by definition, invisible to the outside universe. Now here's where it gets genuinely strange. What's at the center of a black hole? As far as our current physics can tell us, all the matter that falls into a black hole gets crushed down into a single point with no size at all. Infinite density, zero volume. We call this the singularity. This isn't a comfortable answer for physicists because it means our equations break down completely at that point. General relativity, the theory that explains gravity beautifully everywhere else in the universe, simply stops giving useful answers at the singularity. It's a sign that we're missing something, some deeper theory that unites gravity with quantum mechanics. And nobody has fully cracked it yet. So when someone says, we know what's inside a black hole, that's not quite true. We know what our equations predict, whether that's physical reality or a mathematical placeholder for we don't understand this yet is one of the biggest open questions in all of physics. If you got close to a black hole, here's what would actually happen to you. And scientists really do call this spaghettification. Gravity gets dramatically stronger the closer you get to any massive object. Near a black hole, that difference becomes extreme over very short distances. If you fell in feet first, the gravitational pull on your feet would be so much stronger than the pull on your head that your body would stretch, first uncomfortably, then catastrophically, into a long, thin strand of matter, like spaghetti. For a smaller, stellar mass black hole, this would happen long before you even reached the event horizon. But for the truly massive ones, the supermassive black holes sitting at the centers of galaxies, The math works out differently. The gravitational difference across your body would actually be gentle enough that you could, in theory, cross the event horizon completely intact, with no idea anything unusual had happened yet. That's one of the strangest parts. Crossing into a black hole might not feel dramatic at all. It might feel like nothing, right up until it's far too late to leave. Black holes don't just bend space, they bend time. And this is where things get genuinely mind-bending. The closer you get to a massive object, the slower time moves for you relative to someone farther away. Near a black hole, this effect becomes extreme. If you watched a friend fall toward the event horizon from a safe distance, you would never actually see them cross it. Their image would appear to move slower and slower, their light getting redder and dimmer, until they seemed to freeze in place forever, fading out, but never quite disappearing. From your friend's own perspective, though, none of that slowdown would be noticeable. They'd fall in normally and cross the horizon in a completely ordinary amount of time. Two people, two completely different experiences of the same event, both equally real. This isn't a trick of light or perception. It's a fundamental feature of how gravity bends space-time itself. Black holes do not suck everything around them into oblivion like a cosmic vacuum cleaner. If you replaced our sun with a black hole of the exact same mass, Earth's orbit wouldn't change at all. We'd just lose sunlight and freeze, but we wouldn't get pulled in. Gravity from a black hole works exactly the same as gravity from any other object of the same mass. You only run into trouble if you get extremely close, well within a region where the intense gravity and event horizon actually matter. In fact, most black holes are relatively quiet most of the time. The dramatic, glowing accretion disks you see in photos and animations happen when a black hole is actively pulling in nearby gas and dust, which heats up to extreme temperatures and glows brightly before crossing the horizon. But a black hole that isn't actively feeding is just dark and largely harmless from a safe distance. Black holes might actually evaporate. Physicist Stephen Hawking proposed that black holes very slowly leak energy over unimaginably long timescales through a process now called Hawking radiation, over trillions upon trillions of years, far longer than the current age of the universe. A black hole could theoretically lose enough mass and energy that it shrinks away entirely. It's an almost poetic idea. Even the most extreme, light-crushing, time-warping objects in the universe might not be truly eternal. Given enough time, even black holes fade. So black holes aren't holes, they aren't vacuums, and they aren't fully understood, even by the people who study them for a living. They're collapsed stars so dense they break our equations, bend time itself, and remind us how much of the universe is still genuinely unknown. And somewhere out there, at the center of our own galaxy, one of these objects, a supermassive black hole millions of times the mass of our sun, is sitting quietly 4 times the orbit Mercury takes around our own sun, and most days completely unremarkable. If this helped black holes finally make sense, let me know in the comments what you want explained next. And I'll see you in the next one.